So 6.6a will be about the law of cosines, and it sort of is like a natural progression from 6.5, which is the law of sines. We spent a couple of days on law of sines, and it's only natural to be curious. Gee, if there's a law of sines, I wonder if there is a law of cosines, and indeed there is. Notice the lesson goal is identical to what we've been doing for the past couple of days. It's solving triangles. All of these laws of sines, law of cosines, serve one purpose, is to solve triangles, particularly any triangle. Now, you could technically use these for right triangles, but we typically reserve these special laws for non-right triangles. And then that's sort of the idea of the latter half of Unit 6. So I want to start off by recapping the main ideas that we talked about for the past couple of sections. The ultimate purpose of the second half of Unit 6 is to solve triangles. And depending on what type of information we're given, we utilize different strategies. The idea is that when solving right triangles, which is a special triangle, you don't need any fancy rules or formulas and whatnot. You simply use trig ratios. Use your regular SOHCAHTOA, your regular opposite over hypotenuse, adjacent over hypotenuse. Don't fuss about equations and formulas. The only time you need to fuss is when solving non-right triangles. You need to use special rules or laws. And the only one we've talked so far is the law of sines. When do you typically use law of sines? When you have an angle and an opposite side pair. Now, we sort of formalized these situations in yesterday's lesson. If you think back to geometry, you learn about a whole ton of triangle configurations, angle, side, sides, all that fun stuff. Well, yesterday we saw that triangles that are in the side, angle configuration, angle, side, angle configuration, and side, angle configuration all fit this criteria. If I give you a triangle in these three situations, you are guaranteed to have an angle opposite side pair, which means law of sines is unlocked. But of course, the question is, okay, there are a lot more other triangle configurations. What if you aren't given an angle opposite side pair, right? What if you don't have an angle opposite side pair? Right. And what are those situations? Those situations would be the side angle side case. So if I give you a side, if I give you an angle, and I give you a side, angle, side. You can clearly see that we do not have an angle opposite side pair. Or if I simply give you all three sides and no angles. If I don't give you any angles, then it's impossible to give you an angle opposite side pair. So these are the two situations, side angle side and side, where law of sines will not work. You're going to have to use a different rule. Well, what is that rule? What can we develop? Well, just like when we develop the law of sines, or just like in any time in mathematics, if you approach a situation where your current knowledge and your current toolbox does not work or does not fit, you gotta go back to the drawing board. And what is the most basic fundamental thing we did in trig? It was those trig ratios. So we would have to look at these pictures and create right triangles by dropping an altitude. Now I'll say this. If you are really curious as to where the law of sines comes from, please ask me outside of class and I will totally show you. But I think for this lesson, I'm just going to present it and explain how to utilize it, because I'm willing to bet money that not anyone is interested in where it comes from. But if you are the rarity, if you are really interested in the derivation of the law of cosines, please speak with me and I'll happily show you. So again, the idea is that we have the law of cosines. to address the above two situations. So the law of cosines says this: for any triangle, I gotta work on my handwriting, for any triangle ABC, we have, and just like the law of sines, there are three variations. The formulas: a squared equals b squared plus c squared minus 2ab cosine a. Or you could have b squared equals a squared plus c squared minus 2ac cosine b. You could have c squared equals a squared plus b squared minus 2ab cosine c. Those are the laws of cosines. And I will be the first to admit, it is a doozy to memorize. Do you have to memorize all three formulas? No. Do you have to memorize the formula at all? Yes and no. Personally, for me, I find it a lot easier to understand the structure of the formula rather than memorizing all the variations and memorizing the letters. So let's just analyze or break down one of these variations. I'd like to look at the third one because it's the most familiar to us, because the first half is Pythagoras' theorem. And as a matter of fact, the law of cosines is a generalization of Pythagoras' theorem. So let's talk about the structure of the law of cosines, because if you memorize or understand or know the structure, it's a lot easier to remember. So if c squared equals a squared plus b squared minus 2ab cosine c, just like how the area of a triangle formula is just any two sides, that's all we care about. It's just any two sides. That's where the Pythagoras theorem part plays in the role. You notice how in law of cosines you always have one side length squared by himself. Well, this side length here will always be the opposite angle of the cosine that you use. So this guy right here will always be an angle opposite side pair. So whatever angle you use, or whatever side length is by himself, will always be paired with each other. They're always the angle opposite side pair. And that simply means the other variables that are used are simply the other two sides. So if I was to read this formula in like plain English, this is how I would pronounce it. In a triangle, side squared equals the other two side squares added together minus 2 times the other two sides cosine of the opposite angle. So notice how you can sort of speak or say the law of cosines in words rather than arbitrary letters. In any triangle, one side squared equals the other two side squares added together minus 2 times the other two sides times cosine of the opposite angle. You just have to remember these guys are always paired together, and then whatever side you decide to use, these guys here will always be the other two sides. So that's how I personally remember it. Now, yeah, you will have index cards for quizzes and exams, but don't rely on that. Really understand the formula. Other than that, that's it. That's the law of cosines. And then to utilize it is just simply figuring out what pieces you have and plugging it in. So for example, if I ask you to solve the triangle, and the information I give you is x equals 5, y equals 8, z equals 12. Notice how they're all lowercase letters, so what I gave you are all three sides. So I have x, y, and z. Just put them anywhere you want. So x, y, and z. Let's fill in what we're given. We're given side x is 5, side y is 8, side z is 12. So in this particular problem, hopefully it's very obvious, we need to solve for angle x, angle y, and angle z. In this particular instance, it really doesn't matter which angle we solve for first. It just all depends on what you feel like. Let's just go alphabetical order and solve for x first. right? Notice how, again, in the law of cosines, this angle and this side, they're always going to be isolated from each other. So we've made a declaration that we're going to solve for angle x, which tells us in the law of cosines formula, whichever side length is by itself. Notice this guy's by himself and these guys are together. The side length that's by himself will always be opposite the angle you're focusing on. So since we're focusing on angle x, I know that this 5 here should be by himself squared. So let's use law of sines on this opposite angle pair here. We have 5 squared equals, now the moment I declared that 5 is by itself, I'm not going to say y's and z's, I'm going to say the other sides. So 5 squared equals the other side squared minus 2 times the other sides times cosine of the angle I'm interested in. In this case, it's angle x. That's it. Then the rest is just algebra. Use algebra to get x by itself. So I'm going to subtract these guys away first. So that's 5 squared minus 12 squared minus 8 squared. And then to get the cosine by itself, I have to divide out this product here. So divide both sides by negative 2, 12, and 8. And then the last step to get angle x is to use the inverse cosine. So angle x equals cosine inverse of 5 squared minus 12 squared minus 8 squared all over negative 2 times 12 times 8. Notice how when I do this, I actually don't punch it into the calculator until the very end. If you want, you could have figured out what these numbers were at the beginning and worked with that. It's completely your choice. I like to do the calculator work at the end because that, saves me the hassle of potentially rounding and getting the wrong answer. So if you pop this guy into your calculator, you're going to get approximately 17.6 degrees. Oh, little side note. Recall that the inverse cosine will give you answers in the first and the second quadrants only, which means any hidden answers or any possible duplicate answers will be in the third and the fourth quadrants. In the context of solving a triangle, that's impossible. You can't get angles in the third and fourth quadrant. So this is actually why, even though law of cosines looks scarier and bigger, I like using law of cosines to solve for angles, because whatever answer you get, that's the answer you get. You don't have to think about, gee, is there any other angles? So remember from yesterday's lesson, anytime you use an inverse sine to solve for an angle, you have to stop and think about it. Do I have other answers? Is it possibly an obtuse angle? When you use an inverse cosine, you don't have to do any thinking. Whatever answer your calculator gives you, assuming your math was correct, is your answer. So I know that 17.6 degrees is my angle x. Let me just go ahead and write it down here so it's all together. Angle x is approximately 17.6 degrees. Now, the moment I have angle x, technically, I do have an angle opposite side pair. I could use the law of sines to solve for the other angles. But again, if you do that, you have to stop and ask yourself, is it the obtuse angles? Bigger the opposite side, bigger the angle. It's not that hard, but quite honestly, I don't like to risk it. So although we could use the law of sines to solve for angle y and angle z, I'm going to stick with the law of cosines. It's just going to be easier for me. So to solve for the law of cosines, to solve for angle y, that means the opposite side, 8, will be by himself. So side squared equals the other two sides squared, added together, minus 2 times the other two sides, times cosine of the angle. Notice how I'm saying it. I'm just going to fast forward through the algebra because it literally is the same concept, same algebra as angle x, the blue work here. But if you were to go through the algebra, you're going to get cosine of angle y is equal to 8 squared minus 12 squared minus 5 squared all over this mess here. Negative 2, 12, and 5. That way I can take the inverse cosine and get approximately 28.9 degrees. And of course, for angle z, once you have 2 out of the 3 sides of a triangle, you don't need law of sines and law of cosines. Just use the fact that they must add up to 180. So to get the third angle, you simply subtract from 180. So that means angle Z is 133.5 degrees. So there you go, right? So the more of the story on this particular example is not just to utilize law of cosines, but if you use the law of cosines to solve for an angle, you accept the answer as is. If you use inverse sine to solve for an angle, you just have to take a quick second, stop, and think about, and ask yourself: should the answer be acute or obtuse? And truth be told, I'm lazy. I don't want to do that much thinking. If law of cosines can give me the answer as is, I'm going to use it whenever I can. Just for completeness sake, let's just do another example. The previous example was a side situation. You can probably guess what example this is going to highlight. Side angle side, because it's the only other possibility. So suppose I ask you to solve the triangle where angle J is 46.5 degrees, K is 10.5 degrees, or 10.5, and side L is 18.0. So it looks like the letters I'm dealing with is JKL. So triangle JKL, J is 46.5 degrees, K is 10.5, L is 18.0. And clearly we can see that this is a side angle side situation, which calls for the law of cosines. Or you can just ask yourself, can I use the law of sines? The answer is no, because you don't have an angle opposite side pair, so it's law of cosines. So that's the way I sort of figured out for myself, the dreaded question, gee, when do I know when to use what? I always check law of sines first, because that's easy, angle opposite side pair. If I don't have an angle opposite side pair, more likely than not, it'll be a law of cosines problem. So looking at our diagram, I need to solve for angle K, angle L, and side J. I can't use law of sines to solve this, so I have to use law of cosines, and law of cosines does use an angle opposite side pair in a sense where one of the angle or side will be a variable. In this case here, we're sort of forced, just like the law of sines, you don't have a choice. Here, we're sort of forced to solve for J because that's the only real piece of information we have. I couldn't solve for angle K because it utilizes the other two sides, and this is a variable. Same thing with angle L. I really can't solve for angle L because it needs the other two sides, and this is a variable. Solving for angle J is fine, side J is fine, because I do have the other two sides. So let's go ahead and set up law of cosines to solve for side J. So the side squared by himself equals the other two sides squared minus 2 times the other two sides times cosine of his opposite angle, 46.5 degrees. Now this is pretty nice in that as ugly as this side is, all the numbers are filled in. There aren't any variables. So to solve for J, you just quickly square root, right? As messy and ugly as it looks, we are done. So I actually like side angle sides. It is a fast problem. So J is approximately 13.2. Right. So now I have J. I can solve for angle K and angle L. Technically speaking, we have an angle opposite side pair. We could use law of sines. It is a bit faster, but in theory, you could use law of cosines as well. Either way, you're going to be using a calculated value, so there is going to be some error in terms of rounding. Let me just go ahead and show law of sines and the thought process that you have to think about, right? So these are this is what I mean by you got to stop and take a moment to think. So let's use law of sines to solve for, I don't know, K, angle K, right? So I'm solving for angle K using law of sines. 10.5 equals sine of 46.5 over the 13.2 that we found out. So I'll multiply both sides by 10.5. Take the inverse sine, you get K is approximately 35.2 degrees, right? Now we use an inverse sine, so we must think or must consider 180 minus 35.2 degrees, which is, what's that? 549.8 degrees. Now, both of these answers are perfectly valid or perfectly good. There's nothing inherently wrong with them. 35.2 and 149.8. So look at our original picture here. We have this theorem in geometry that says the smaller the side, the smaller the opposite side, the smaller the angle. Notice that we did solve for side j. Side j is 13.2. Of the three side lengths, notice how this is the smallest side length, which tells us this should be the smallest angle. So I know it's impossible for this angle to be 149.8 because it would be bigger than this guy. Also, 149.8 added to 46.5 would be way too big of an angle. It's bigger than 180 degrees. So I know that it's not possible. It can't be the obtuse angle. It has to be the acute angle. So we must consider this guy, but not possible. So I know this is angle K. And of course, once you have 2 out of the 3 sides of a triangle, you don't need anything fancy. You can just go ahead and subtract from 180, angle L, to get the other's angle. So that angle L is 180 minus 46.5 minus the 35.2. That's going to give us 98.3 degrees. So we solved that triangle. So law of sines is doable. You can do law of sines with these problems. Just take a quick second, 5 seconds maybe, to consider the obtuse angle if possible. That's it. That's law of cosines in the 2 cases, side, 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 and side, angle, side. I do have a last example here, just as a word problem, because I always want to include at least one word problems in these notes. So let's just do this quickly and see the logic behind it. So suppose I told you that a car travels along a straight road heading east for 1 hour, then travels for 30 minutes on another road that heads northeast. If the car maintains a constant speed of 40 miles per hour, how far from its starting point is the car? And when it comes to law of cosines, these are classic problems. You have an object, a car, a ship, a person, whatever. They travel in a certain distance for a certain time, change directions, how far apart is from start to finish. So this is a very classic question. We need a diagram. We need to draw it out. So the car starts somewhere. Here's the car. According to the story, it travels east. So east is perfectly to the right. And then it changes directions and goes northeast. Now, when in math, we are very specific with our terminology. We don't say northeast just as a rough approximation. Oh, and up and to the right. If you hear the term northeast, you can bet money, you can be confident that that is a mathematical 45 degrees. So in our picture here, I don't guess. I know for a fact, since it said northeast, that this is halfway between the quadrants, 45 degrees. And the question is asking how far apart is start from finish. So it's looking for this distance d here. Now I need to fill in some side lengths, and the important information is that it goes east for 1 hour, 30 minutes on another road, and 40 miles an hour. And so this is sort of like common sense logic. Let's do the first pathway, right? Going eastwards. If you are going east for 1 hour at 40 miles per hour, I hope everyone knows or can agree that they've traveled 40 miles. Like, no duh. 40 miles an hour for 1 hour is 40 miles. On the northeast path, he only goes 30 minutes. That's half as far, or half as long. So I know it's going to be half as far, 20. So now we got to go ahead and solve. Now, this is the same logic that we use in any math problem. Focus on what you're asked to solve for, in this case, side D. And since it's a triangle problem, I ask myself, what triangle is he a part of? Well, hopefully everyone can agree he's part of this triangle. Then I want as much information as possible with the highlighted triangle. Well, notice how the 40 and the 20 miles are a part of the triangle. The only other information they gave us, this 45 degrees, is outside of the triangle. And I don't want that. I want information inside the triangle. Well, we need to remember in geometry that a straight angle adds up to 180. So if the outside or the exterior angle is 45, the interior must be 180 minus 135. Lo and behold, look at what we have. We have side angle side. And that just cries. That's classic law of cosines. So solving it should be a piece of cake. Side squared equals the other side squares added together minus 2 times the other two sides times the cosine of the opposite angle. And I hope everyone can agree that to solve for D, you just take the square root of that ugly mess. And if you take the square root of the ugly mess, you get about 55.9 miles. Right? So law of cosines, side angle side, probably the easiest and my personal favorite problems to solve because, well, it's simple. So that's it. That is the other tool you have in your toolbox to solve triangles that are not necessarily right triangles. Good luck.